Hello, my name is Beth Dixon, and this is a video series based on Vicki Borlaug's PowerPoint presentation on discrete distribution, the population mean, standard deviation, and expected value. I wish to thank Mrs. Borlaug for allowing me to use her PowerPoint to make this set of videos. This is part one of this set of videos. Statistics relies heavily on its notation. Trying to understand statistics without learning the notation is like trying to herd cats. I cannot emphasize it enough. Notation is important. So let's review our notation, most of which you will have seen before. X is your data value. Sigma is used as an operation sign and tells you to add together the values that follow whatever follows the sigma sign. The sigma here is the Greek capital letter. Just like our alphabet has capital and small letters, in the Greek language, sigma is a capital sigma, and the little O with a hat is the small sigma. And so we have two sigmas, and please keep them straight. It will make life so much easier for you. Next we have mu, and it's like a cursive U or a U with a stick on the left-hand side. And this is the Greek letter mu. Remember that Greek letters tend to go with population values and English letters go with sample values. So mu is the population mean. And again, that's the Greek letter mu. Next, we have a symbol that is read sigma squared, and it is the population variance. It really squares the Greek letter sigma, and no, we haven't made a mistake. This is the lower case of the Greek letter. So both the upper and lower case form of the Greek letter sigma are used. Sigma without the squared is next, and that is the population standard deviation. Notice this means that if we square the standard deviation, we will get the variance. And inversely, if we take the square root of the population variance, we will get the population standard deviation. This is the third place that we see the Greek letter sigma. The capital letter means to add together. The lower case is for the population variance and standard deviations. The squared for the variance, without the squared for the standard deviation. It is time for an example to put things into practice. Example 1. Given the probability distribution, find the population mean, variance, and standard deviation based on the table here to my left. Think about a way that this could be a real-life problem. Maybe it's the age of players on a little league team, or the number of months a child is before they walk, or the number of donuts that pass inspection from a batch of 13 donuts. It doesn't really matter. It just reminds you that problems have a basis for reality, even if we just give you the numbers. We will need to find the mean, the population the population variance, and the population standard deviation. And remember, that's mu is the Greek letter and the Greek letter sigma, so keep those straight. It will make life a little easier. First, we want to look at the table and think about what that table really means. X is the data value. So under the X column are the data values that we have in our distribution: 10, 11, 12, and 13. The P of X column represents the probability that we have for each particular data value. So as we look at that first one, what that is telling us is that 20% of the time we will get a 10. The next value or next row tells us that 30% of the time you'll get an 11. 40% of the time you'll get a 12. And only 10% of the time you'll get a 13. Next, let's look at a graph of that same information. Notice the X values are along the horizontal axis and the probabilities are along the vertical axis. Ms. Borlaug illustrates this graph with a line and a dot this way, drawn with a line from the 10 up to the 0.2 mark, illustrating that 10 happens 20% of the time. We can graph each of the next values in the same way: 11 up to the 0.3, 12 drawn up to the 0.4, and 13 drawn to the 0.10. Remember, our task is to find the population mean. We can visualize that this would be a point around here. Why? The population mean, or mu, is the balance point of the data, and we can see by looking maybe that that's where it would balance. We want the weight, and that's in quotes, to be the same on both sides of the mean. If you make selections from this population over and over again, the population mean is also known as the long-term average. So, for the population average, here is the numbers to calculate it. Where did they come from? Well, think back to what we said to start with. 20% of the time you get a 10. 30% of the time you get 11. 40% of the time you get 12. 10% of the time you get 13. Now do the arithmetic. This gives us 11.4 as the population mean. Notice this matches our graph, and we can visualize the mean as that balance point of our data. Now to develop the formula for the mean. Mu equals the sum of x times P of x. Sigma means to add together. X times P of x indicates that we should take the data values multiplied by their probabilities. So notice how that matches what we have done to find the population mean. We multiplied the data values by their probabilities and then added them together. I will pause here for the first part of this set of videos on counting. Please, not on counting, on population mean. Please watch the next video where we'll pick up on finding the variance and the standard deviation. Thank you for watching this part, and if you need more help and are a Walter State student, please come by the Math Lab in MBS 222.